So much like we have our normal stress strain diagram with our normal stress sigma and our normal strain epsilon, we can also do the same with shear stress. If something is subjected to just pure shear, so you have some block and it's subjected to a shear stress. So now it shears and moves into some shape like this, where we have that relationship with gamma over 2. We have pi over 2 minus gamma, we said was shear stress. We can have a shear stress strain diagram as well, just like we had for normal stress. It looks very, very similar. A few minor differences. It's generally a little less detailed, our shear stress strain diagram. So in our shear stress strain diagram, we're going to have our shear stress tau on the y-axis, and then gamma is our x-axis. And it's going to have a linear elastic region, just like our regular stress strain diagram, but then it doesn't typically go through a yielding phase. It typically goes straight from the linear elastic region into strain hardening up to failure, or not failure, up to the ultimate shear stress, then releases down some to failure or fracture. So here we still have this linear elastic region. It goes up to the proportional limit. Right, so this is the proportional limit of the shear stress, and this is the proportional limit of the shear strain at this point. And then it goes up until the ultimate shear stress, and then comes back down to our, say it's right about in there, tau failure. Happens at gamma failure. So very, very similar, right? We can pull a lot of the same information off of this diagram as we did with the one before. And just like we had our modulus of elasticity for our linear elastic region in the normal stress strain diagram, we have a shear modulus of elasticity that we call G. So in this region, G is the shear modulus of elasticity, or you will also hear this called the modulus of rigidity. Modulus of rigidity, how rigid something is, how much it is susceptible to shear, how rigid it is. Both of these are G. These are totally interchangeable ways of describing G. But it's much like our modulus of elasticity, where the definition of G is going to be the shear stress over the shear strain. And typically we use these proportional limit values because we can find them pretty easily on our stress strain diagram here. So tau over gamma, shear stress over shear strain. Now, interestingly, this can also be related to the modulus of elasticity. There is a relationship. We have an equation relationship using Poisson's ratio. So there is an equation for shear modulus of elasticity equals the normal modulus of elasticity over 2 times 1 plus the Poisson ratio, Greek letter nu. Now, all of these are known values, G, E, and nu, the Poisson ratio. All of them can be found in those common tables. So if we look at just average mechanical properties of materials, materials on the side here, it has modulus of elasticity and modulus of rigidity. And then it gives you, you know, your yield strength for tension, compression, and shear. They are different. Here's your ultimate strength, tension, compression, and shear. And then over here we have the Poisson ratio. So these are givens that we can look up for a given material, but we can also use these relationships if we want to calculate things between shear stress and strain. Let's look at this example that has some of the information we can pull off of a shear stress strain diagram. So we're given a little shear stress strain diagram in the left side, and on the right side, this is actually the block of thing that is being stressed, right? So this little 2x3x4 block is experiencing this shear stress, and it wants us to find the shear modulus of elasticity, the proportional limit, and ultimate shear stress, and then also find the max distance d that the block can shear elastically, and what magnitude of shear is required for this to happen. So the first three are just going to be things that are pulled from our diagram. We don't really need to do much math with these. They're mostly given to us. It's just a matter of identifying them. For example, the shear modulus of elasticity. As we just talked about, that shear modulus of elasticity, G, is going to be the shear stress over the shear strain, and only in that elastic region. So that elastic region goes up just to the proportional limit. So we can use the proportional limit shear stress over here and the proportional limit strain and plug those in to get our modulus of elasticity, the shear modulus of elasticity. So 52 over 0.008. And I believe I forgot to put units on this chart, but it's in KSI is the shear stress, and then radians, of course, is always our units for shear strain. So when we divide those, we get units that are the same as our top guy. So our units will just be in KSI. And that gives us, when I punch it into the calculator, 6,500 KSI. Pretty easy, right? Just identifying what's on the chart, plugging it into the equation that we know. And even simpler, it asks us for the proportional limit, which we just used to find this shear modulus of elasticity, right? It's this proportional limit where we change from linear elastic into our non-linear region, non-elastic region. The proportional limit was given to us there as 52 KSI. And then it also asks for ultimate shear stress, which is given to us again just in the chart. We can read it right off the chart. Ultimate shear stress is 73 KSI. So we've answered over half the questions just by reading things off the chart. That'll be sometimes it's a big part of it. You can't get anything right until you know how to read a chart. So our next portion asks us to find the max distance d that the block can shear elastically. So the max distance means what is the most shear that it can go through, right? What's the greatest strain, that distance it'll go through before it starts behaving non-elastically. So we know from our chart that the maximum shear strain this can experience, the most distance it can go, is this 0.008. After that, the strain is too great. It starts deforming. It's no longer acting elastically. So the max elastic shear strain, is 0.008. And then we know, looking at our little block that they gave us in the first place, if we're finding that d, where the angle is gamma because it's a shear strain and the distance is d, we can use small angle theory. Now that we have this angle, we can use small angle theory and this side length of 2 to find out what d is. So our small angle theory that said S equals theta R, or in this case, if we replace it with what we actually have over here, the S is the distance, so D is the angle, gamma, times R, which is the side length over here. This radius R is 2. Or in this case, 0.008 times 2. So that the distance is 0.016 inches. And that's just because this 2 over here was in inches. Right, so 0.008 is an extremely small angle. So we can use our small angle theory to just use this little triangle and get that relationship. You can use the tangent, like tangent if you want. It's going to give you almost exactly the same answer if you treat this like a right triangle and use tangent. But it's so small that your answer is going to end up about the same either way. So that's our distance D here from the shear. And our last portion says, what is the magnitude of V for this to occur? So our magnitude of V for this to occur means I'm going to need a relationship between where this is occurring and the shear stress. Or sorry, the shear itself, the shear force. But I spoiled it a little bit because that relationship is the shear stress, right? Because if we look at this, the location where this strain occurs, we can relate directly to where the stress occurs. So at this strain of 0.008, the stress is going to be 52. So looking at our shear stress is the shear force over the area equation. I know that at 0.008, my shear stress is 52. And I know the area because I'm given this block up here. So let me rearrange this to say V equals tau times A. So my tau is 52 KSI. And now I need the cross-sectional area, and that's the area that's being sheared, that's experiencing that shear force. So again, the shear goes along the same plane, right? It's parallel, it like shears on the same plane as where the force is acting. So this is where the shear is being felt. This is the area the shear is acting on. And we're given it's 4 inches here. This is 3 inches, so it's a 4 by 3 inch area. So area is 4 inches times 3 inches. And I pop that into my calculator and it gives me 624 kips. Since that's the shear stress that's occurring at this shear strain as given from the chart. Then it was just a matter of using the information in the block to find out what the actual shear force would be required to get that. So let's take a look at one more example using these charts and things together, using these properties of materials together. So in this last example, we're looking at a bike tire that has brake pads acting on the tire to slow it down. So we have these brake pads, the tire is made of rubber. Each pad has a cross-sectional dimensions of 20 millimeters by 50 millimeters that are contacting on the tire, and a shear modulus of elasticity of 0.2 megapascals. If 70 newtons of friction force is applied to each side, determine the average shear strain. So it sounds like a lot, but I want you to, before we work through this together, go ahead and pause the video and try to work it out on your own. Try to work through what are you given, what are you looking for, what can you use. You don't actually need the tables or anything for this. Just use the equations that we've talked about today and see if you can figure it out. So now we'll look at this together and see how you did. So we have this 70 newtons of friction force on each side of the tire here. So looking at my tire on the side, I have 70 newtons on this side and 70 newtons on this side. So it's in double shear, as we've talked about. And so if I were to look, let's just look at one brake pad, for instance. I can find my shear stress. My shear stress is the shear over the area. So for just one of these brake pads, the shear stress would be the shear of 1, so the 70 newtons, over the area. And again, it's the area that's contacting on that tire. So it's not this 10 millimeters by 50 millimeters as it is here. It's this 20 by 50 ratio they give us. So even though we can't see that 20 millimeters, that's what's actually contacting on the tire there. So that's where the shear stress is being applied. I'm going to do a quick unit conversion to meters just to keep everything in its base unit. So I'm going to assume it's rectangular in cross section since it gave me just a 20 by 50. And I can calculate my shear stress is 70 kilopascals. Now, remember what I'm finding here is the average shear strain. So since they gave me that modulus of rigidity, I can use that to relate my shear stress to my shear strain. So G is shear stress over shear strain. Or I can write this, since I'm finding the shear strain gamma, is the shear stress over the modulus of rigidity, which is my shear stress we just found is 70 kilopascals over the modulus of rigidity, 0.2 megapascals. So I actually might want to go ahead and convert this. I'm going to convert from kilopascals to 70,000 pascals, and then from megapascals to 100,000 pascals. So I end up with my average shear strain here is 0.35 radians, where shear strain always has units of radian. And that's my final answer.